Hi everyone, this is Isabel Harrison. Welcome to today's ASIG webinar. Our moderator, Rob Gramlich, will be kicking things off in just 1 minute. Rob, I think you can get started whenever you're ready.
Okay, thank you, Isabel. Welcome, everybody. Good afternoon. I'm Rob Gramlich, president of Grid Strategies, LLC, and board member of Americans for a Clean Energy Grid. We're here to provide you with some really important new information from a recent study about large-scale transmission development in the United States. This is brought to you by ASEG, and we can move to the slide describing the Americans for a Clean Energy Grid. You can find us at www.cleanenergygrid.org. This coalition has been together since 2008, or this organization that works to educate the public and policymakers about transmission. Many different interests are involved in this from a diverse array across the electric industry. We will, on the agenda here on the next slide, we'll be introducing quickly our speaker and panelists and reviewing key findings from the study. We'll have some moderated discussion to make sure we get the key points out, and then we'll take your audience questions and try to get answers. You can engage with us through the webinar software here. GoToWebinar. On the right side, you should have a panel where you can send in questions. I'll be looking at those questions and directing them to the appropriate panelist or panelists as you may specify. You can also tweet about this as we go with the hashtag SEAMS study. There has been some activity on there, and we encourage you to become part of that conversation. Without further ado, why don't we go to the introductions here and tell you who we have. First of all, Jay Casberry, who I've known for many years. I consider him one of the foremost transmission planners in the country. Southwest Power Pool, where he works, has been a national leader in building transmission, and that has been responsible for a lot of reliability, efficiency, and clean energy integration improvements in the south central part of the country. Jay serves as Director of Research, Development, and Tariff Services there. And he was co-chair of the Technical Review Committee for this SEAMS study, so he will be presenting highlights of the study. We have two commenters, Michael Goggin, also from Grid Strategies with me. Michael is a member of the Technical Review Committee and has been following the study since its start and has served in similar capacities with dozens of renewable energy integration or just transmission planning studies around the country over the last 10 years. He also serves on the NERC Planning Committee, and we'll talk a little about reliability and resilience. And then finally, Jesse Jenkins, who is a postdoctoral fellow with the Harvard Kennedy School. You probably see Jesse if you spend any time on Twitter looking at energy issues. He's very active there. He's in the New York Times today, but he's also all over the latest academic research from his work at MIT and now Harvard on decarbonization pathways and generation portfolios going forward. And so he's going to comment mainly about transmission's role And in that framework, how does it fit relative to other portfolios and industry developments on the decarbonization pathway? So with that, why don't we dive right into it? I should have said, these slides will be posted on the ASEG website, and this webinar is being recorded, so you can share with friends, and if you can go back if you miss anything. And the ASEG website already has an extensive set of slides from another presentation at Iowa State this past summer. So there are materials there. If you want to go in and find any particular question right now, you can go do that. But why don't I turn it over to Jay to hear his key findings and what this study was all about. Jay, you there?
Thanks, Rob. Can you hear me okay?
Great.
Great. Thank you so much. And thanks to ASEG for letting me be part of this. I'm with Southwest Power Pool. I'm an engineer, and our job is to keep the lights on in the U.S. plains. We serve the grid from the Canadian border down into eastern New Mexico, Texas Panhandle, and then over into eastern Texas and Louisiana even. So the majority of the U.S. plains are served by Southwest Power Pool members. We are an RTO, a regional transmission organization. We operate a market, and we're responsible for grid planning. I want to move on to the next slide and kick this off. I want to share some slides that I've extracted from the deck that Rob mentioned, that is posted on the ASEG website, that Aaron Bloom, who was the project lead for the National Renewable Energy Lab, used at the TransGridX 2030 symposium that was in Ames, Iowa in late July. These slides are a little bit different because they are finalized in the report, but I want to go through and share some slides about the background of the study, why it's important to Southwest Power Pool, and then get into the results, and then I look forward to the discussion. So let's move on. Quickly, I do have a disclaimer and I've got you a link to the website that's out there for the NREL study. I would encourage you to check that out. There probably will be some new papers posted there, as well as some other information that you'll find of interest. This disclaimer is that things will change, but I think that what we have seen so far, that the models and the data are and the results are pretty well definitive. It's how it's presented, and we're waiting on that to be finalized. So let's move forward. Let's talk about the study. So the Department of Energy funded this study, being led by the National Renewable Energy Lab. It was one of the grid modernization lab collaborative efforts, which involved industry, significant amount of support from industry. MISO, the Mid-Continent ISO, and Southwest Power Pool provided the chairs of the Technical Review Committee. We had significant involvement by everybody that's affected by the grids in the east and the western parts of the U.S. What I'm concerned about, and you'll see why quickly in the next couple of slides, is we've got some aging infrastructure that actually ties together eastern grid and the western grid, that we need some answers to the life cycles of those pieces of equipment and how we're going to treat them and what we're going to do with them. So we got DOE to fund this study to look at 4 scenarios of how the eastern and the western grids of the U.S. could be tied together. And we looked at several DC solutions, the status quo, which are basically keeping the current capacity of the back-to-back ties. We looked at modernizing the ties and upgrading them, or actually including big HVDC links over the top of the seam, or even a macrogrid overlay, which is a big HVDC network. The results were very promising, but there is more work to be done. So let's go forward and show you a nice graphic of why this is important. This actually shows the 3 grids in the U.S., the Western grid, the Eastern grid, as well as the Electric Reliability Council of Texas. Those grids are separated by back-to-back HVDC converter stations that are relatively small based on the size of those grids. This study is actually looking at the interconnections between the Western grid all the way out to the Pacific coast and the Eastern grid all the way to the Gulf Coast and Atlantic coast of the U.S. This is a little bit of a simplification because the grids actually extend into Canada, but we're just looking at this from a U.S. perspective. One thing to keep in mind is that the solar resources in the U.S. are obviously the best in the southern parts of the U.S., as you see on this graph. And the wind resources, the land-based wind resources, are best in the plains. And where those high-quality renewables intersect is right along the seam between the eastern and the western grids, as you see on this map. This study didn't look at the ties with ERCOT because those ties have been upgraded or replaced in the last few years. So those ties have been addressed in terms of life cycle and what we're going to have for the next 15, 20 years. That's not true for the seams between the east and the west grid, which are shown on the next slide, which shows the capacity of the HVDC ties. They're relatively small ties between the eastern and the western grid. They were installed basically in the 70s and 80s primarily, and but they certainly are very much small aging infrastructure compared to the size of the eastern grid and the western grid in the U.S. You know, the National Academy of Engineering called the power grid one of the greatest engineering achievements of the 20th century. And I don't think that this is necessarily what we want in the 21st century. So we need to decide, how do we want to create a vision that could be bought off by all the stakeholders on what the grid should look like between the eastern and the western grid. And that's what this study did. So let's go forward to slide 7. These are the actual models that were used, concepts of the design scenarios that were created. The first is status quo. We don't do anything to the back-to-back ties between the east and west grid. The second, scenario 2A, is we actually upgrade those ties at the current locations and expand the AC system to accommodate the optimal transfers. Design 2B is where we let the DC ties expand and we add 3 big DC links that were from pre-selected nodes across the seam. And design 3 is the macro grid, which is a big HVDC network that would allow significant flows of power across the U.S. Let's move on. So those were the scenarios that we looked at. How did we do it? We did it, and these are a lot of acronyms here, I apologize. But we did a co-optimized generation and transmission plan that Iowa State led on to look at what would the resources look like in terms of wind, solar, natural gas resources, as well as what the transmission system should look like for those 4 scenarios. Based on those results, we ran production cost models using a tool called Plexos at NREL to look at how would the economics of these build-outs play out in year 2038. And finally, we were going to do some reliability analysis on the back end by the Pacific Northwest National Lab to make sure that these systems were secure. Let's go forward to the next slide. One of the key things about this study is that we had a common set, a timestamp data set for all resources. For the wind data, for the solar data, for the load data, for the entire eastern and western grids, as well as updated transmission models that we all agreed to, which is a big effort because we haven't done this for forever. And that's why it was so important to move forward with a good data set and to do this kind of optimization analysis. Let's go forward. So the first part of the expansion plan was to look at the resources. And here you see the resources in 2024 by class. You'll note that the hydro resources and the nuclear resources did not change, but we let the models optimize the amount of coal, natural gas, solar, and wind resources in these models. There was no consideration of storage assets in these simulations. For design 1, 2A, 2B, and 3, you see for the 2 scenarios, base case and a high variable generation case, significant changes to the amounts of solar resources that were optimal in each scenario at the end of the 2038 optimization period. So that's the amount of capacity shown here. This data doesn't show that much change between the base case design scenarios 1, 2A, 2B, or 3 for all the resources, but you do see some significant changes between the high VG cases and the base cases with respect to wind primarily. Let's move forward. This is showing the results in 2038 of how much AC transmission was added to these cases, and this is not maybe the best optic or the best metric, but it does show that very little or no HVDC transmission was added in design 1, and some in 2A, 2B, and more in design 3, which was the network for all of the cases. What you do see is that for under a high VG scenario, we see tremendous amounts of AC expansion, and even 90 gigawatts of AC expansion in the base case for any of the designs 1, 2A, 2B, or 3 is significant. So there's a lot of AC expansion that is optimal under any case, and DC actually helps out the AC system too. Let's move forward. So for the results, all cases are predicated on a future where we can build multi-regional transmission projects. That's not necessarily what happens today, but this shows the benefits of doing so. Design 1 has no new transmission on the DC side. The generation mixes change substantially in all the cases under either scenario. These results are not definitive, but they are indicative of direction. So we need to take them and move them forward to secure additional analysis. Let's go forward. This is just showing one of the issues that I see in the base case. You see in this graph, the yellow is the amount of new PV added primarily in the California market versus Southwest Power Pool or the Mid-Continent ISO. The one thing you do notice, though, in this case is a significant amount of curtailments, at least in SPP, and that is indicative of a less than optimal case. So the results that are shown here actually have significant amounts of inefficiencies that are driven by curtailments for Southwest Power Pool. So there's more work to be done. Let's move forward. This is one of the nicer graphics that actually shows a lot of information of what could happen. Along the bottom, you see a time scale of a week. And what you're seeing is wind power moving out of the plains to the western grid during the night. And during the day, you see solar power moving from the western grid into the eastern grid during the day. And this is a diurnal cycle that you see in virtually any scenario where we have high amounts of capacity linking the grids together. We can't do that today because of the old aging infrastructure that is a curtailment. Let's move forward. I don't want to spend a lot of time on the next slide, but these are the results, and we could, the bottom line is the benefit to cost ratios that are shown on the next, well, we'll talk about the benefit to cost ratios later, but so the economics of these projects are pretty compelling. That's the takeaway. Under a base case or a high VG scenario, you get benefits that exceed cost over the planning horizon, this 14, 15-year period, which is a pretty short time period for transmission assets. Let's go forward. Initially, we wanted to look at the production cost benefits of the base case relative to the change cases under all these scenarios. And what you do see are significant amounts of production cost savings in year 2038, which would go forward in time under the base case or the high VG cases. Let's move forward. This is some high-level takeaways for the benefits. All of the designs produce benefits that exceed cost. We're only looking at a 15-year period for the BC ratios that are on the top of this graph. These savings will continue in the future and they will grow. That's the important takeaway from this. So there's a pretty good payback for these investments in these simulations. Let's move forward. There's additional work to be done. One, we can always improve our models. Two, we could always expand the scenarios to look at additional things, as well as get additional weather cases to run to look at resiliency, as well as to get into the reliability assessments that are really important for some folks. But I want to focus on some of the findings, which is the next slide, and then wrap this up and get input from the other folks. So is there value to increasing the transmission between the east and the west grids? Yes, there is. It's significant. And increasing the transfer capacity between those interconnections, status quo is probably the worst case. So we need to do something. How we're going to do something and how we're going to decide on what the shared vision of the future grid is subject to additional work and debate. So what are the options for replacing these old aging facilities? There are many, but do we replace them in kind? Do we relocate them? Do we bypass them? You know, there's options here, and we need to study more of these. So there are big opportunities for new cross-country transmission. You get significant benefits from the grid if you can transfer capacity and energy and ancillary services across time zones and take advantage of diversity of renewable resources. And there's probably benefits that we haven't thought about. And I think resiliency is probably one of those that's very timely at this time. A couple more slides, I'll wrap up. These are SPP's observations in slide 20. So we need to do more work. We need additional analysis. The status quo is the least desirable case. These models are showing that we need to spend a lot of money on AC alternating current transmission lines and not necessarily just DC between the grids. These models also probably need to reconsider the voltages of the backbone facilities in these simulations. That was one of the constraints in the model that probably is resulting in some suboptimal results and understating the benefit to cost ratios of interconnectedness between the grids. The last bullet is really important. These are we've got harmonized models and data sets now that are really important for us to do supplemental analysis and have some dialogue about what does this mean and where do we go with it. So my last slide is slide 21. And what are we going to do? First of all, we got to finalize the interim report. It's moving forward and should be getting closure soon. The other thing I think we need to do is to investigate additional solutions. Do we relocate the back-to-back ties? Do we relocate the HVDC terminals in these links? Do we even look at possible AC or hybrid AC and DC solutions? I think technically and economically, those results would be very promising. But regardless, we do need to scope out supplemental work to inform the regional planning that's being done today under Order 1000 and to help shape the dialogue about the next steps. At the Department of Energy, there's a major initiative going on right now to create a North American resiliency model by Bruce Walker. I'd like to find a way to leverage that effort and additional supplemental analysis for maybe a SEAMS 2 study to help us work together on getting good models, good data, and getting good recommendations and things to consider at the regional level. And finally, I think we need a shared vision that will help us all get a roadmap to address aging infrastructure in the U.S. We've got billions and billions of dollars of assets out there that were installed in the 50s through the 80s, and we need to replace those, and we need to work together to find out what is the best way to do that and which facilities might want to be considered for right sizing. That concludes my prepared remarks. I look forward to the dialogue and the panelist discussion. Thank you.
Thank you, Jay. That was great. An impressive volume of material in 20 minutes. We're going to turn now to Michael Goggin, who I introduced before. If you're just joining late, we went through the slides from Jay Casberry on the SEAMS study. Again, the slides are on the ASEG website, cleanenergygrid.org. There's a longer presentation from which these are drawn, so you can look up anything you might have missed. But Michael, we'll turn to you to talk about, you've been following transmission investment and reliability issues for some time and the various studies over the years. How does this fit in? What should people take away from this study?
Sure, yeah, I think, and thanks Rob and thanks Jay for the excellent introductions to the study. It was a pleasure participating on the review committee for the study. I think we're really doing groundbreaking work here that is looking at optimizing generation and transmission under a range of future policy scenarios. And I would note, I think that one of the biggest takeaways for me is just the very impressive benefit to cost ratios and large consumer savings you would see from such a large transmission investment. So looking at the larger transmission build in these the high variable generation, the wind and solar cases, the investment we're talking about is only about a $12 to $19 billion in incremental investment above what was needed in the base case, just to kind of keep the lights on as load grows and into the future. So, you know, for about $12 to $19 billion, that's about what we spent on the last World Cup, to put in perspective. In exchange for that investment, over the first 15 years alone, you're looking at a savings of between $30 and $48 billion. So, you know, you can do the math there. It's a benefit to cost ratio of about 2.5 to as high as 3.3 to 1. So basically for every dollar invested, you're getting back between $2.50 and $3.30. So that's obviously a very attractive investment. And that's just over that first 15 years. As Jay noted, the study also looked at what the ongoing savings would be beyond that period, and it's about $2 to $4 billion per year additional savings, and that goes on indefinitely. You know, transmission lines last half a century, maybe even longer. So, you know, these are going to continue paying dividends for decades and decades past this kind of initial benefit to cost ratio period. And you know, this is really, you know, valuable, and a lot of this savings comes from things that aren't quite intuitive. It's just making the power system more efficient through having this large transmission grid. When you've got adequate transmission. You can share operating reserves and planning reserves, basically how the power grid operators use power plants and how many power plants they have to build can be done much more efficiently if you have the ability to move power from region to region and use diversity in electricity demand as well as electricity supply, particularly as you add variable and uncertain wind and solar. Having this kind of large national grid becomes increasingly valuable. But it's true even without that. We've got a lot of diversity between different parts of the country in terms of when their peak energy demand is. And I think, it should be noted that, as Jay mentioned, that, SVP and others have looked at the range of benefits that transmission provides. And I think this study is conservative in only looking at some of these pretty purely economic consumer savings. There's a number of other things that, benefits to consumers, such as more reliable and resilient power. And, the expansions that were included here, particularly these high voltage direct current transmission lines, have a lot of capabilities to really make the grid more flexible and respond to any type of disturbance, whether it's an extreme weather event that affects a certain region, or an intentional attack of any kind, a cyber attack or physical attack, or just whatever, unexpected occurrence. All of that transmission is really valuable for having the flexibility, the redundancy that allows you to reroute power with HVDC lines in a fraction of a second and allow regions to better lean on other regions in a time of stress. And that I think was not, it's very difficult to kind of quantify those benefits, but they're very real and quite valuable. Large scale blackouts cost on the order of $10 billion. So this is, if we can even prevent one of those, it's that alone is an extremely valuable benefit. And there's other benefits as well, just having the flexibility and the optionality as fuel prices change. We don't know how that's going to play out over the coming decades. As carbon costs, I think, have to be factored in, and then as well as changes in renewable costs. There's just tremendous amounts of uncertainty across all parts of the power system, how demand is going to change with electrification of vehicles and other things. All of this creates a lot of uncertainty about what we're going to need and where we're going to need it in the future power system. And transmission provides a solution to all of that by allowing power to be moved in time and space from where it's produced to where it's needed. So all in all, I think, this is a very good first cut at trying to figure out benefit to cost ratio of transmission. It showed a really compelling numbers, but even those numbers I think are conservative compared to what we'll actually see play out. I think the analogy is kind of looking back at when we built the national highway system under President Eisenhower. At the time, it was mostly justified on national security justification that in the event of war, we would need to mobilize troops, and it was kind of modeled on what had been observed in Europe during World War II. And of course, in the 50 years since then, we've used the highway system for transporting goods and services and just going on vacation. And obviously, we've all benefited massively, many times over, from that investment in ways that couldn't have been imagined when it was first envisioned. So I think we're talking about the same type of national network that will pay very large and often unexpected dividends for many generations to come. Cool. I look forward to the further discussion.
Great, thank you, Michael. So very large and both quantifiable and unquantifiable benefits here overall. Jesse, we'll turn to you now. You've been studying decarbonization pathways, and we're already getting a couple questions in here about whether large-scale transmissions such as this scenario or these scenarios would reduce carbon. Are they a significant part of the decarbonization agenda for the industry or not?
Yeah, thanks for including me, and I'm happy to provide some perspective on the role of transmission in our transition towards a low-carbon power system. I think if you look across the literature and various studies from national laboratories and academic institutions and others that are trying to explore how we might transition most cost-effectively to a lower carbon and cleaner electricity mix, virtually all of them include a substantial expansion of long-distance transmission lines. And whether that includes strengthening ties across the eastern and western grids, or HVDC transmission superhighway that would overlay on top of our existing alternating current grid, or just a substantial expansion of current of AC transmission between regions, they all traditionally include a significant expansion of long-distance transmission lines. And I think it's interesting to note that that's true in scenarios that rely heavily on, or almost entirely on, variable renewables particularly, but it's also true in scenarios that that include a more diverse mix of resources, including potential expansions of nuclear power, of carbon capture and storage with natural gas or coal, and other dispatchable renewable resources like geothermal or biomass that rely less substantially on weather-dependent wind or solar resources. So there are definitely economic gains and potential environmental gains to be had from transmission expansion as we think about moving towards a low-carbon energy system. One thing I will note, however, is that there are some alternatives to transmission expansion. And there are scenarios that are more dependent on achieving greater extensions of our transmission grid than others. The scenarios that rely most heavily on transmission are perhaps not surprisingly those that rely most heavily on variable renewable resources, particularly wind and solar. If you think back to that map that we saw at the beginning of the solar and wind resources, then the best areas in the United States, those areas, of course, are clustered in the south and southwest for solar, and in the Midwest and Plains regions for wind. And then when you think about where the population centers and large electricity demand centers are in our country, they tend to be close to the coast in the Great Lakes region, and our existing grid was constructed not to tap into wind and solar as our natural resources, but to tap into coal and hydropower resources primarily. And so the existing grid isn't really configured to move power from those sites to where we need it in a system that is much more tapped into American clean energy sources in the form of wind and solar. And so just for that reason alone, we're going to need to think about how to expand transmission to tap into renewables. But there's a second reason why scenarios that are heavily dependent on wind and solar need transmission, and that's to spread the variability of those wind and solar resources across the country by tapping into more diverse assets, diverse wind and solar sites where weather patterns aren't so strongly correlated. And that can play a really big role in reducing the amount of total installed capacity needed for wind and solar assets and the amount of curtailment or wasted energy that goes along with those scenarios. Scenarios that are less dependent on transmission include those that tap into a greater amount of energy storage. So depending on how much energy storage we think we might have in the future or how cheap it is, transmission can move energy around in space and storage can move it around in time. And to some degree, those are partial substitutes for one another, although not perfect substitutes. It would be ideal to have both in the future system, both storage and transmission. And scenarios that tap into resources that aren't weather dependent and can be located more adjacent to demand centers, of course, are also less reliant on transmission. And so, chiefly that hinges on whether or not we think we are likely to see an advanced nuclear energy industry emerge in the 2030s and beyond that might be able to allow us to tap into carbon-free energy sources that are located much closer to population centers rather than far out in the Plains region or the Southwest. So that's, I think, the overall look from the literature. And I think it's interesting to note, too, that regardless of whether you care about climate or decarbonization, there are strong economic reasons to expand our transmission capacity, and that's been shown time and time again. I was struck by leafing through Aaron Bloom's slide deck that's available on the ACEG site. And there's a whole series of studies highlighted there dating all the way back to the 1920s of national scale transmission expansion plans that were unveiled. And of course, most of those never came to fruition despite those economic benefits. And I think it's worth discussing later in our agenda here why that has been the case, why we've struggled in the U.S. to build out the kind of really long distance multi-state transmission infrastructure that has clearly made economic sense for almost a century. And yet we've still been unable to sort of realize that grand vision. And I think it's important to get to the bottom of that as we think about how to transition to a low carbon energy system. So I'll leave it there for now. Thanks.
Great, thank you, Jesse. And thanks for mentioning the NREL team, which did and led much of this work. They've done incredible work over the years. And it's really, as you said, not so much even about renewable energy necessarily, despite their name. It's about the system and how you operate a large-scale system reliably and efficiently. Both looking at, they do a lot of work on the grid operations and markets as well as the transmission side. I wanted to follow up on Jesse's point about storage, and we're getting some questions in here about, it seems to be people's favorite different technology sources. So I guess the big question is sort of, do we still need a lot of transmission if we develop resource X? And X is, some people think a lot about distributed resources, rooftop PV and other behind the meter sources. There's sort of a vision of the grid that's very popular, of much more small scale and distributed. So that's one. Number two is grid operations technology. So we can squeeze more out of the existing grid with dynamic line ratings, power flow control, topology optimization, and other things today that maybe weren't quite so viable 10 years ago. Third is storage. Jesse already covered. Love to see if the other panelists agree with how Jesse characterized that one. And then offshore wind is another one we're getting two questions about, and the role of natural gas. So again, the larger question is sort of, if whoever's paying for this, and I want to get to that question later, but is it wise to put up capital given what might happen with DG storage, grid operations, offshore wind, natural gas, et cetera, or might these be stranded assets? So I don't know who wants to start on that. Jay, do you want to start, and we'll go back through in order?
Yeah, that's fine. Thanks, Rob. A lot of good topics there. I'd like to make a couple comments. One about offshore wind, and with respect to, do we need the grid if we could build a lot of offshore wind? We've done some studies, at least in the Eastern interconnection. The Eastern Wind Integration Transmission Study was done a few years back by NREL again, and with a lot of industry support, that actually looked at significant offshore wind development as well as onshore wind development in the Eastern grid. One of the key findings of that study was that we still needed and could justify major transmission expansion across the interconnection, even if a lot of offshore wind were developed along the eastern seaboard. I think that surprised a lot of people, but the economics, when you look at the weather patterns, the diversity, and the flow, and the resource quality and the timing of the resource for onshore wind is much different than offshore wind. And those resources actually complement each other. And if you had a grid, you would be able to take advantage of that and lower costs for everybody and get more green renewable energy to markets. So I just want to make that comment to start.
Yeah, this is Michael. I could try to take on, I think I got all the questions down. So, on the question of the value of transmission relative to these things that are presented as transmission alternatives, I think transmission is always going to have an essential role because it's the only resource that can move energy across geographic space. Energy efficiency, demand response, energy storage, all of those are very useful for moving energy in time. Basically, you store it and then use it later. But that doesn't solve the fundamental problem we have, particularly with large amounts of location-constrained wind and solar resources that are located in places where not a lot of people live. And as a result, we need transmission. Demand response, energy storage would only be useful in those situations if they're located on the same side of the transmission constraint as the renewable resources. So having, for example, batteries or demand response in a major city, and you're trying to deliver wind or solar via transmission from a remote area to that city, those resources don't help with the transmission constraints getting from the wind and the solar to the city. They need to be on the same side of the constraint, and just given where people live, you're not going to have demand response and at least behind the meter storage out in those locations in significant quantities. I think you can do lots of useful things with energy storage to complement transmission, and this was borne out in work that's been done by a fellow at NOAA who was formerly at NOAA. He's now at Vibrant Clean Energy, named Chris Clack. He's done several analyses for the state of Minnesota looking at kind of this interplay between transmission and storage. And what he's found is that there's actually a lot of synergy there that storage gets higher utilization and more value when you have transmission. That allows it, basically what you would do is you would deploy both transmission and storage. And then the storage uses excess wind that would have been curtailed or excess solar. And then when there's available space later on, several hours later on the transmission line, it then just discharges, and therefore you get a higher utilization of both the storage resource and the transmission line. So you actually see more use and more value for storage in those scenarios because of that complementarity. So I think we need to be doing both of these. And similar, that would be my answer with the question about technologies to improve the utilization and the operational timescale of transmission. So dynamic line ratings, other technologies to do advanced topology control, power flow control, all those are extremely useful in making sure that we get all the megawatt hours we can across the grid we have, and as we build new grids to optimize that investment. So yes, absolutely all those things, but we still need transmission because it's the only resource that really can move energy in geographic space at the scale we need. And that I think brings me to the final question about distributed generation and your rooftop solar. And I think we're still going to need a large amount of transmission, even in scenarios if we have a large amount of behind the meter PV. You get the duck curve issues that we've seen in California, as well as just a variety of overproduction during the midday hours, and transmission with the time zone diversity it brings and the climate diversity, as well as the resource diversity as you move a larger geographic space, combined with storage, becomes extremely valuable. So I think in all these scenarios, no matter what happens in all these exciting technology fronts, we're still going to need transmission.
Great, thanks. Jesse, you want to comment on that?
Yeah, I'd be happy to. I think maybe a couple of points. I'll first start about sort of complementarity and substitution, I guess, of transmission and other assets, and then I'd love to dive in about distributed resources and rooftop solar as well. So on the first point, I definitely agree with Michael and want to clarify that whether you have storage or dispatchable low carbon resources closer to load centers or offshore wind closer to the East Coast or West Coast population centers, that may reduce the amount of transmission that it makes sense to build out, but it's not going to eliminate it. And so I agree with Michael that there's this fundamental need to reshape our electricity grid to tap into the kinds of resources that are going to power the 21st century grid, and that is going to include much more American wind and solar resources than in the past, where our existing grid was built out, as I mentioned, largely to tap into hydro and coal resources in the 20th century. So, it's a fundamentally different asset base, a set of U.S. natural resources that we're tapping into to power our future grid. And that's going to require reconfiguration of transmission systems and build outs to areas that previously haven't had much transmission capacity. And I think about the renewable energy zones that were designated in Texas to sort of say these are areas where we know there's strong wind resource in West Texas and the Panhandle, and we know these are far from cities. And so we're going to set these out as zones. We're going to have tenders for transmission expansion to tap into them, and then we'll figure out how much transmission we need to bring wind energy from those regions back to the cities. And I think that's the kind of thinking that we need, nationally. We know where the best wind resources are. We know a lot about those weather patterns and how they blow, and we can simulate where it makes the most sense to build out these assets. And then we have to solve the tricky problem of figuring out how to site and pay for these lines to tap into those areas. And I think that's where things get difficult. And to the degree that we can reduce the need for politically contentious wind or solar projects through other assets like solar or offshore wind, I think that's where we start to see some of the substitution on the margins. And so, for example, in New England, where I am, and across the Northeast, there, is an increasing push to tap into offshore wind. And I think one of the main reasons for that is due to the difficulty we've had in the region building out long distance transmission to tap into wind and solar resources that are much stronger outside of the Northeast. And so because we've been unable to build out long distance transmission to much lower cost wind or solar resources elsewhere, we instead are turning to offshore wind or to rooftop solar within the region, which are perhaps quite a bit more expensive, but circumvent the need for siting transmission. And so there's this interesting tension between the economic case for transmission and the political challenges and difficulties of siting and agreeing on cost allocation for new transmission lines. It's a really important tension. Just one more point, I guess, about the role of rooftop solar and distributed resources versus transmission. This is actually the focus of my dissertation topic at MIT, was this competition between centralized and distributed resources and the development of modeling tools that can help look closely at that trade-off. And what I came away from that research with was a clear sense of the trade-offs that matter relate to a trade-off between economies of scale, which argue for building much larger resources, large-scale solar farms, for example, rather than rooftop solar farms, because larger systems are more cost-effective in terms of labor and balance of system and installation, to the point where it can be twice as expensive to build a rooftop solar system at a residential scale in the U.S. As it is to build a large multi-megawatt utility scale project. And so on the one hand, economies of scale argue for building larger projects, which necessarily mean tapping into more transmission. On the other hand, you have locational value that's captured by distributed resources that can be sited closer to areas of demand, and therefore avoid impacts on the transmission grid, like distribution losses, transmission losses, and constraints or congestions, or the need to expand either the distribution or transmission grid. And so in areas where there's substantial locational value, which exceeds the economies of scale penalty that you face, it makes sense to make distributed resource investments. And in areas where economies of scale outweigh those locational value, it makes sense to invest in large-scale assets. And I think from my modeling, I've seen that on balance, economies of scale currently win that in most circumstances. But in either case, there's a mix of the two that's needed. There will be locations where rooftop solar or distributed solar at a larger scale is cost competitive when you look at the full system cost and the trade-offs there between economies of scale and locational value. And there will be cases where large-scale renewables win in that trade-off. And so even as we build out a more distributed future than we have today, we're going to need more transmission at a large scale as well to tap into more cost-effective renewable resources where we can.
Perfect. Thank you all. So I'm hearing large-scale transmission is robust to a variety of futures with different resource portfolios, so that there's probably not a high likelihood of stranded assets, which is what regulators should worry about. But I think also relevant to that question is, what are the barriers? So let's get real here. Could anybody actually build a grid like this? Jesse, you mentioned challenges in the Northeast. Jay, you all and your SPP colleagues and your neighbors in MISO and your neighbors to the south in ERCOT all built quite a bit of transmission, but it wasn't really the interregional sort or interconnection sort. So can we really go bigger to interregional and interconnection? If the barriers are so severe, then maybe the policy guidance is just build as much as you can, given the benefits and benefit cost ratio and the robustness to various futures, and rather than nickel and diming it, sort of let those natural constraints limit how much we can get. But I don't know, is that the policy guidance? Well, let's talk about the barriers and how one could actually build lines like the ones we're talking about. Jay, do you want to start?
Yeah, thanks, Rob. I'd love to. There are barriers, let's be real here, but I think there's opportunities too. And like I mentioned earlier, I think there's a lot of aging infrastructure that was built on the seams, basically, of the U.S. grids to bring large amounts of coal-fired capacity from mine mouth plants to load centers heading west and heading east, but no consideration of potentially tying those networks together. One of the comments that Jesse made was the challenges of paying for these lines and siting these lines. Who's going to pay for it? That is always going to be the hardest question to answer, and we'll have to really look for some leadership from some key people in the policy realm to help us with that. But in terms of siting lines, I think there's an opportunity here to take advantage of these old existing lines in key corridors that may have not been considered. SPP has had limited success in building interregional projects and getting them approved. but we are making strides. We've got projects in the works between us and Associated Electric Co-op. We are making great strides in working with MISO to improve our processes and hopefully get some joint projects between us and the Mid-Continent ISO in the next few years that will get approved and then built. It takes time to build these projects, so we need to have long lead times in our planning horizons. But I think there's significant economies of scope and scale when it comes to transmission too, and the value you get. Now, whether it's an AC line or a DC line, there's different characteristics and attributes of each. But we need to consider all the options going forward. Hope that helps.
Yeah, this is Michael. I would I would add that I think transmission is one of these kind of classic public good problems where there's a tragedy of commons where everybody kind of recognizes this is extremely valuable and to society, but there's just difficulty of figuring out who pays and how do you recover the cost of that investment. And it's just like the same thing we do with police and fire and military protection, hospitals, all of that provide these valuable public goods. And therefore, you need to come up with a policy that requires people to pay for that. And we've seen in SCP and ERCOT and MISO, they figured that out. They did the CREZ model in Texas, they did the highway byway cost allocation in SPP, and they did the multi-value projects in MISO. And that worked. We got a large amount of transmission built in those regions over the last 10 years. Now we just need to take that model to the interregional scale. As Jay mentioned, right now there are a lot of challenges in getting interregional transmission built. There is some success in getting smaller incremental projects, but nothing really of the size and scale that we really need to efficiently take advantage of the opportunities for interregional transmission. And so I think that the time is right at FERC for revisiting Order 1000 and looking at some of the I think that did a lot of good work on the kind of intra-regional transmission planning and cost allocation, but didn't really solve the inter-regional piece. And I think going back and revisiting that or doing a new rulemaking that does come up with a way so that regions can have a way to share the cost of transmission that benefits them both makes sense and would really be in the interest of the country. Right now, I think that the process just doesn't work. The projects have to pass this triple hurdle where each region has to be proved beneficial to both regions as well as each region individually. And you just don't see a lot of large-scale projects making it through that process for a variety of reasons. So streamlining that. And then also on the permitting side, we've seen a lot of very promising proposals for interregional transmission lines, including direct current transmission lines get shot down because of a single state along the middle of the route objecting, and basically that ends up killing the line. And so I think we do need to move towards a more streamlined siting model, something similar to what we have for natural gas pipelines, where there is some federal authority that can be used if a state does not act within a certain time period. But anyway, I think we've got clear models of how we can solve this problem. We just need to implement them.
Yeah, I think to echo that, I think that the real key challenge is at the policy level at this stage, and the question is whether there's a sufficient set of benefits and a clear sense of public good from large-scale transmission expansion that would justify some changes to federal policy to potentially give more siting authority or lead siting authority to the federal government as it exists for natural gas pipelines for these sorts of large multi-state public interest projects that could facilitate the siting process in a way that doesn't require individual permitting processes for each individual state that a project passes through. I think in particular for regions like the Northeast with much smaller states, that becomes a really, really interesting and key challenge to coordinate all of these different states that a line may pass through and to go through the process required to do that. If you're a very large state like Texas or California, there are some lines you can build within your boundaries without having to deal with that. But in general, all these plans for large scale transmission expansion include a lot of multi-state lines that really face this key challenge, which is that you not only have to pass the siting and permitting process for each individual state along the path, but you also have to figure out a cost allocation arrangement that works between all the states involved and the RTOs involved. And I think that, the second, areas that, if Order 1000 did require interregional transmission planning exercises between the RTOs, and those haven't even occurred, and in some cases have identified mutually beneficial projects across the RTO boundaries. But you still face a stakeholder challenge, which is that if an individual RTO can find a project that benefits its alternative project that benefits its region more than the inter-regional project, so even if there are net benefits for both regions for an inter-RTO connection, if there's a project that benefits an individual RTO to a greater degree that exists within its own region, they still have incentives to pursue those kinds of projects and forget the interregional collaboration. So there's some really key challenges here to tackle. And I think the only way we're going to have any interest in doing that is if we can really see the key benefits. And so studies like this, the SEAM study, studies that Chris Clack and others have been doing to look at the role of transmission in a low carbon future, those are really important to help lay the foundation for that discussion and elevate this as an important matter of public policy.
Great, thanks. That's a good way to sort of zoom out for our last minute, maybe a minute or two for each of you to wrap up here. You mentioned sort of the national interest, and we're getting a couple questions about other countries because physics and economics tend to be pretty similar. We're not the only country that has large, remote, clean resource areas. And the questioner here is noting that China built a total of 19 UHV lines at a cost of several $billion each, an additional 10 UHV DC and 28 or 27 UHV AC lines that are under construction or in development. So other countries seem to be doing this build out. There's talk in, I think, Europe still. I don't know what the status is about kind of a large offshore supergrid network. Where if we can get over these hurdles on planning and cost allocation, is this really what other countries are doing and should do, and are we even sort of set up for this in this country? I'll just open that up to any of you. We've got 2 minutes left.
Yeah, this is Jesse. Maybe I'll start. So yeah, I've seen studies, deep decarbonization studies for various reasons, and they really all share the same unifying feature, which is that if we want to tap into greater shares of wind and solar, which we will in virtually any deep decarbonization scenario, the question, I guess, is to what degree, they all include transmission expansion at a large scale. And so I've seen studies for Europe and North Africa and Middle East, for China and Southeast Asia that, include these kinds of long distance links. And I think countries like China or Russia that have a large, internal landmass and a large, powerful central government can do a lot of this on their own. Without some of the challenges that we're talking about. But my thesis advisor, Ignacio Perez Arriaga, is a Spaniard. And as we talked about these challenges, in my studies, and I complained about the balkanized nature of U.S., transmission siting policy, et cetera, with 50 different states, he'd like to remind me that, I think it's hard to cite transmission and allocate costs in a country with 50 states. How about in a place with 30 different sovereign countries, like the European Union? So I think, we can count our blessings in some ways, that we do have a federalist system here with some authority at the federal level, some at the state level. We're not dealing with individual, discrete, sovereign countries trying to tackle these problems. I think in many ways, Europe faces even greater challenges around siting and cost allocation than the United States.
Yeah, this is Michael. I think, the examples are all correct that, China and India are building massive amounts of extremely high capacity, high voltage transmission. And those voltages, some of those capacity on those lines is, double even some of the biggest lines that were envisioned in this study. So, I think, the key conclusion we're seeing is that in countries that are, efficiently kind of optimizing the system, they're building transmission as big as possible and as much of it as possible. And I think we can get there as a country. Historically, we built the highway system, which was this massive cooperation between federal and state governments. We've built interstate transmission. One of the most cost-effective lines we have is the Pacific Intertie that allows seasonal diversity and resource diversity between Pacific Northwest and Southern California. And we've built long haul transmission. We've built massive, the hydro dam system and the accompanying transmission, and the electrification of the country was all done largely through federal leadership in the 1930s and 40s and on. And so, we have done this stuff, and there's no fundamental reason that we cannot return to building, very beneficial public infrastructure. And we need to do this, not just in the electric sector, but across sectors. And I'm hopeful that this is kind of a bipartisan vision of investment and benefits that I think can be realized.
Great. Well, we're
Jay,
going to stop it there. There is a way to send in your questions on the last slide here, info@Clean Energy Grid. I encourage anybody to do that. We can direct them to the right people. Really appreciate everybody's participation. We had a great crowd of people and a lot of good questions that came in, and I really want to thank Jay, Michael, and Jesse for their contributions today. With that, we'll call it a wrap and hopefully be in touch. Thanks, everyone.